Well, hello there. Good morning, good afternoon, good evening, good everything. Hope you're doing fantastic. Hopefully, you guys are done with lesson 14 on introduction to arrays and are ready to move on to lesson 15, which is all about processing arrays. So, doing something with the things that you have inside of your lists. Note that there are a few vocab terms. You have for loops, linear search, binary search. So you do want to jot those down in your journals. I have no idea when I'm going to be looking at those things, but hopefully sooner than later. There's new code, but hopefully when you look at the code that it looks somewhat familiar because you have done for loops before. For loops were introduced in Unit 3 when you guys were playing around with that turtle thing. And then you guys have done functions also back in Unit 3. And I think in Unit 5 you used them just a little bit. But in this lesson, you're going to really learn how to create a function that you can use whenever you want to find the minimum value of something. So that's kind of cool. With the GIF that I have below, it's just showing how a list is processed and just going through each index and printing out each element at that particular index as it is iterating through the list. So now we're going to have Mary, log that, and then we iterate to the next thing in the list, which is Susan, the next thing in the list, which is Jane, there she is, and so on. So that's what we're going to be working on for lesson 15. So what you should know by the end of lesson 15 is you should be pretty comfortable using a for loop to be able to process a list, to essentially iterate through the list. You should be able to write some code that implements linear search on an unsorted array of numbers. And you also need to be able to distinguish between linear search and binary search. So we'll look at that later on. But you should be able to explain what both of them do and when you would use those, which one is most efficient for whatever application that you're going to be using it for. And then you should be able to write a function to find the minimum value in an unsorted list of numbers, essentially using linear search. So I thought this was a cute cartoon off to the side here. It kind of goes, it's a play on a for loop. So you got the little kid here who's refusing to eat. Hey, for mama, for papa. Kid's like, oh, hell no. And then mom's like, well, WTF, no, you will. So I'm going to shove this down your throat, essentially. Here's a for loop. Throat 5 times. So shove it down the throat, more, and then baby finally is going to throw up on the 5th iteration. So ha ha ha. I know you guys find my computer science jokes lacking in humor. I think they're funny though, so meh. Oh my gosh, remember this. How frustrating was this? So this goes way back to Unit 3. I think they introduced this concept way too early. A lot of you guys were really frustrated. And there were some kids that were like virtually on tears. Like, I don't know how to do this. It was hard. Okay, so we're using this like weird human machine language, which was like mimicking machine code. You didn't have a whole lot of options in terms of what you could use to code, looking for, in this case, the lowest value card that's on the table. So what's interesting about this, if you think about it, let's apply what you guys have been learning in starting with lesson 14 on arrays. So we have a bunch of cards. So 4, 8, 7, 3, 6, so on. And then look at what's above it. You have a 0, a 1, a 2, a 3. Those are indexes, essentially. So if you look at the cards, it's kind of like a list. So you have list, maybe like var cards equals 3, 8, 5, 9, 2, and so on. And then you should be able to find the minimum value in that list. And that's what you were doing here with this weird code. But now you're going to have, I think, more powerful tools in a for loop to be able to find the minimum value. And so you guys are going to be working on that in lesson 15. And then also remember when you guys were in lesson or unit 3, you guys were playing with Turtle, and you guys used a for loop to create some pretty cool repeating patterns. So with this, we're just kind of creating this pattern by just repeating the same code, but just altering it slightly by turning it right to. But we're doing this 500 times. So you get this really cool little pattern here. So hopefully you remember that. So here's a definition for a for loop. So a for loop, typical looping construct designed to make it easy to repeat a section of code using a counter variable. The for loop combines the creation of a variable, a Boolean looping condition, and an update to the variable, one statement, which makes that kind of a cool thing. So let's look at what we got here. Let's use this example right here. So we have three things going on. We've got the creation of a variable. So our variable is right here, okay? And we're initializing the variable to 1. Our second thing we have here is a Boolean looping condition. All right, so this loop is going to keep going until this condition is false. So until I is less than or equal to 10. And then we have an update to the variable, which is our counter, which is this right here. So this is 2 and this is 3. So we have all three of those elements there. And so essentially what's going to happen with this particular piece of code is it just counts from 1, because we started with initializing it at 1. And then each time through, it's just going to keep printing out the next number until this condition right here is met. So less than or equal to 10. So it's going to count all the way up to 10. The flow for a for loop. So the flow on this is kind of interesting. So using the same idea from the last example, but we're just going to make it up until 5 so we don't have to write this out 10 times. So we're initializing the variable to 1. All right, so that's right here. We're initializing it there. Our condition that we're looking at is right here. So as long as I is less than or equal to 5, then we do another iteration. And so we're incrementing with this. So incrementing, and that's what that is. So the first time we go 1 through it. The second time we go 2, 3, 4, 5, and then we stop on 5. Okay, so let's go through the flow chart and see how that all works. So we have the initialization. Okay, so 1. The condition is 1 less than or equal to 5. It is. All right, so we're going to write down a 1, and then we're going to increment. So now we're on 2. Is 2 less than or equal to 5? It is. So we need to write, let's go this way. We need to initialize, and then we just check the condition. Okay, so then we're going to write down 2. So we're here again. Then we come back up here and we iterate, and now we're on 3. Okay, so then we go back here. We initialize the variable. We look at the condition. Is 3 less than or equal to 5? It is. So we write a 3. And then again, we increment, and then we're on 4. And then we just keep going through this until we get to 5. So note then, when we get to 5, let's do 6. So we get to 6. Okay. We look at the condition. Is 6 less than or equal to 5? It is not, so it's greater than. So that is where the loop will stop. And then we come out of the loop. All right. So then it stops at 5. And that's how the flow works in a for loop. So let's take a little listen to our friend Brendan and see what he has to say about processing lists with loops.
With lists, we can begin to store lots of data, and we can also think about writing code to process that data. For example, a list of the pixels in an image can be processed to change their colors to give the image a unique filtered look. A digital song file is actually just a list of waveform samples and can similarly be processed to apply digital effects. We know that computers are great at repeating commands in the form of loops, so when we want to process every item in a list in a similar way, we can use a loop to iterate through every item and take some action with it. Let's look at how we use loops to process lists. First, we can make a while loop to run a specific number of times by using a variable called count. This loop will run 6 times. We also know that lists have numbered indexes starting at 0, and since the variable count stores a number, we can use count as our index into the list. And since count changes every time through the loop, starting at 0 and going up by 1 until 5, this gives us a mechanism for accessing every item in a list. An easy first step when processing lists is to write a loop that prints out all the values in the list to make sure you are seeing everything. Let's do that here. We'll add a console.log statement in the loop and make the loop condition more general by removing the hard-coded value 6 and replacing it with the length of the list. Now, if the list size changes, our loop will still print everything out. Let's run it. This kind of looping structure, one that uses a variable to control the number of times the loop iterates, has 3 basic components to it. Creating and initializing a variable to use as a counter, some condition that checks the value of the counter each time through the loop, increasing the value of the counter by a set number for each iteration. This kind of structure is so common that many languages include the for loop to do just that. The for loop combines these components into a single line of code for convenience. The standard setup of a for loop looks like this. There is a lot going on here, but you can see it has the same basic components as the while loop above. It creates a counter variable called I. While I is less than 4, add 1 to I every time through the loop. You might read a for loop out loud like this. For variable I starting at 0, while I is less than 4, I++. You can think of I as shorthand for index, and I++ is shorthand for increase the current value of I by 1. The value of I will come in handy when we use it to access each item of the list, just like we use the counter variable in the while loop. Note that I is just a convention and you can name it anything you want. Let's look at an example of using a for loop to go through every item in a list and doing something with each item. Here we have a list of red, green, and blue values for a very small image. We could brighten it up by adding 50 to every number in the list. In each iteration of the loop, we are getting the current value stored in the pixel list at index I, adding 50 to that number, and then updating the value at that same slot in the list to the new value. So the first time through the loop, I is 0, pixels at index I, or pixels at 0, is 28, 28 plus 50 is 78, pixels at index 0 is updated to be 78. The next time through the loop, I is 1, so pixels at index 1 will be accessed and updated in the same way. This will happen for each item in the list. With a for loop and a list of values, you have an easy way to process all of the items in the list. This is a foundational concept in computer science you will see over and over again, and it unlocks the power of dealing with lots of data.
Thank you, Brendan. All right, with processing arrays. So this is one of the most common things that you're going to be doing with a list, is you're going to be iterating through a list. That's the processing part of that. And for loops are one of the most common ways to do that. You can use a while loop to actually go through a list as well. So for loops allow programmers to easily iterate through all elements of an array, and it's really easy to code and write, so that makes it easy. Algorithms that process and search through lists, which we're going to be looking at the linear search and the binary search in a little bit, but those are there because you have all this information in a list, and so what do you do with it? So you might need to find a name, for instance. So if you have a list of names, or the closest store in a particular area, to compute grades, to rank people, search for a song in a playlist. So there's a lot of applications, like real world type applications for processing arrays. And like I said, all data processing will most likely use a loop, be it a for loop or a while loop at some point to be able to access all of the elements inside of the array. All right, so here we have a list, and we have a list of animals. We have a monkey, a lion, a wolf, a polar bear, and a giraffe. Did I spell giraffe right? Does giraffe have two F's? I don't think it does. That's like a giraffe. A giraffe. Yeah, that's a new animal, giraffe. All right, I think I'm going stir crazy here. Okay, so our giraffe. All right, so let's look at the loop. So we want to iterate through this loop, and we want to like take inventory of all the animals that are at the zoo. So we set our variable at 0. So what this means is we're going to start at index 0. And then here's our condition. As long as we're not at the end of the list, we are going to move through the list one by one. Okay? And then we're just going to print it out. The zoo contains, and then this here is referring to whatever index you're at, and it'll print out the element that is in that particular index. So the first thing that it prints out as it goes through the flow of the for loop is monkey. Okay, are we at the end of the list? We're not. So we're going to go here, and we have a lion. We're not at the end of the list yet. So then we have a wolf. We're not at the list yet. So we have a polar bear, and we're not at the list end of the list yet. So we have a giraffe. The giraffe. Now we are at the end of the list, so the loop stops, and then that's it. Easy peasy. Whoop. So what are some things you can do with a JavaScript array? I was playing around with this a little bit and just came up with a few cool things that I thought might be interesting for you. They might want to use at some point. We're going to use the same list of animals with our giraffe. I will talk about this flag thing in a little bit. That's one's kind of important. So you can sort, okay? When you sort a list, if it is a list of strings like I have here, then it's just going to sort it alphabetically. So that's what's going to happen. So if you look, I console logged it, and that is right here. So you can see that this then is in alphabetical order. Starting now with giraffe. All right, so we're sorting that. Oh, I should say also that when you sort numbers, that if you just use this right here on numbers, it's going to convert the numbers to a string, and you're not going to get the results that you want. So there's a couple of parameters that you need to use, and I will show you that once we get to looking at, that was the binary search. All right, so you can sort. Hooray for sorting. This right here is what I just showed you, where we're just looping through the list and we are just writing out what is in the zoo. Okay, so all of the elements of the list. This one right here, we're printing out every other element starting at index 0. So for that one, notice the variable is initialized as 0. Our condition is the same. The only thing that I changed was this right here. So we're going to start at 0, element, or I should say index 0. And then we're going to skip to index 2 and index 4, and if we had a 6 and whatever, but we only have just a small amount of elements inside of the list. So what this should do is it should print element 0. Let's count them out. 0, 1, 2, 3, and 4. So it should print out element 0, element 2, and element 4. Okay, or here's the list again. So these ones right here. And then lo and behold, there they are. Woo! All right. So now let's say we want to search for a specific element. We want to know if there's a wolf in the zoo. Okay, we could have a list of 5,000 animals. Okay, and we don't know if there's a wolf. So let's look for it. We're going to initialize just the same. We initialize the loop to start at index 0, see what's there. And we're still looking at the entire length of the list. And then we keep going through the list until we get to the end of the list. Now, a little bit different here is I have this if statement. So if the animal at that particular index that's being examined is a wolf, flag true. So notice up on top, I created this flag equals false. So here, I'm saying that if the condition is found, that now we're going to say that's true. So then if this is true, okay, if this is true, which now it is, so if flag is true, then we're going to say wolf is found. And when we run it, that's exactly what's going to happen. Why? Because there is a wolf in the array. Now, if there was not a wolf, this true that's here would have remained false. And so therefore it would have printed what's in this else statement, no wolves here. This is our linear search, which I am going to talk about right now. So searching and sorting algorithms. I took a whole class on this actually. It was on algorithms and data structures. And so we learned a lot about how to write different algorithms for processing arrays. So one of the most frequent things you do with arrays is sort and search. Searching arrays for specific elements is one of the most common things you do with arrays. Sorting algorithms put elements in a list in a certain order. Most frequently, sorting algorithms will order the list numerically or alphabetically. Okay, so we have search in arrays. That's one thing that you can do. And then also you have sorting algorithms, and you will have searching algorithms that search through arrays. They're both algorithms, okay? Just steps to do something. So we're searching, we're sorting. There are several search and sorting algorithms available. So for sorting, you have what are called bubble sort, selection sort, insertion sort, merge sort. And if you take AP Computer Science A, I'd be willing to bet that you will be learning how to do those different types of sorts. And then for searching, we've got the linear search and the binary search. So why do you have all these different sorting and searching mechanisms? Well, because it depends. It depends on what you want to do. It depends upon the size of your array. It depends upon what type of an array you have. It depends upon what you want to do with it. Essentially, you want to use the sorting and searching method or algorithm that is the most efficient for whatever that situation happens to be. So we're looking at the most efficient search, okay, and sorting method. That's what you're looking for. So thankfully, at this class, all you need to know is linear search and binary search. So here's a definition for linear search. So linear search requires starting at the beginning of the list, looking at every single item one at a time and continuing until the element is found. Okay, this is easy, right? So you've got a list of 1, 2, 3, 4, 5. Okay, so we have those elements inside of the list. If I want to know that if there's a 4 inside of that list, then I can just look at this one, just loop right through it, right? And then if the condition is true, okay, and then we say yes. Okay, you can also, it doesn't have to be sorted like that. So 3, 10, 50, 6, 1. All right, so I'm looking for the number 6. So same thing, I just look through with a for loop each of these things until I get to the true condition, and it's there. So linear search is really easy. It's easy to code, and it makes a lot of sense. So linear search is simple and effective, but, and a big banunu. So really this is only good to use on relatively short lists. Okay, so like examples I showed you up there, that's easy to go through that. However, What if you have 1,000,000 elements? Okay, so you're looking for the number 1, and you have 1,000,000 elements. You have no idea where that number 1 is going to be. If you're lucky, if you're using linear search, so you might have 6, then a bunch of other ones, and then you got, 1,000, and then maybe like a 9, and maybe a 1 here, whatever. And then let's go out. Why does it keep doing that? So then we got 99,000 here, and then you just keep going out. So you have 1,000,000 elements. Okay, so maybe this 1 is at element 50, we'll say. So that's pretty easy to go through with a regular old for loop and just look through each one until you get to the number 1. But think about if the number 1 was the very last element in the list. It could potentially take a really long time then to actually go through every single element individually, one by one, until you actually get to that 1. So when you have a really long list or a really big array of some sort, then a linear search is probably not the best. Okay. However, if there are 1,000,000 elements in the list and the element searching for is not in the list, that's the worst case scenario. Okay. So, you're looking for the number 1 in a list that has 1,000,000 elements, and then it spends all the time to sit there and go through the entire list, and then there's not even a number 1. Okay, so that's the worst case of scenario in terms of efficiency. But even if the element is in the list, but at the end, a linear search on a long list is not efficient and probably should not be used. You need to know that. Okay, that's part of what you need to know for the AP test in terms of efficiency. So here's our example of a linear search. This is what I already showed you guys. So we have our animals array, and then we got all these animals in here, and then we're just searching. We're just going literally animal by animal. Okay, so animal by animal. And we're looking for wolf. So, and this is it, when you are at that particular element, you're looking at it. If that particular element at that particular index is wolf, remember you're setting that flag to true, and then you're moving to here. Okay, so we're literally going element by element by element or index here until you get to the end. And then if it's not there, in this particular case, the flag is still false. So then it would print no wolves here. But because we do have a wolf in the list, then the wolf is found. And hurrah. Okay, so this is linear search. It works great on a list that is small like that. But again, if you had a zoo of 700 animals, then this may not be the best way to do a search in terms of computer efficiency. So then that brings us to a binary search. So your definition for a binary search is that you have a sorted array, and this is very important. So you have to have a sorted array, and it looks for a specific element inside of the sorted array. If the element is present in the array, the search returns the index of the element. Okay, so it tells you what index it's at, like what number. Otherwise, it returns null, which is 0. Because the array has already been sorted, the search can compare the target search element to the element in the middle of the array, eliminating half the search range at a time. Super efficient. So we're going to watch a short little video from the CS50 course that Harvard puts out, which does a good job of explaining binary search.
The phone. You don't see these things too often, though the college still seems to have these in the houses and dormitories. But back in the day, when you wanted to use a phone like this, there was no electronic address book in your cell phone. Rather, you pulled up something known as a phone book. And these phone books had had about 1,000 pages typically. They were sorted from A to Z, and you simply had to find the right page to find the person you're looking for in order to find their name and their telephone number. Now, how do you go about looking up someone in this book? Suppose my goal is to give my friend Mike Smith a call. Well, how do I go about finding Mike Smith? Well, it's a very reasonable approach, if naive and inefficient, would be start here, and start flipping to page 4, to page 5, to page 6, and to sort of linearly, along a straight line, go through this phone book. And even though it's going to be incredibly tedious, if Mike Smith is in this book, I'm eventually going to reach him when I finally flip to the S section of this book. Now, of course, you don't need to be a computer scientist to know that this is a stupid way of solving this problem. What would a typical human being do? Well done. So you would flip to the middle, right? So you'd flip roughly to the middle, look here, and I seem to find myself in the M section. Okay, so M is clearly not what I'm looking for, and Mike's to the right, so to speak, of this section, and as some of you have seen before, we can literally now proceed to tear this problem in half. You really shouldn't be that impressed. Tearing it down the seam is actually not that hard. The real people do it this way. But down the seam, we now have two problems, each of which is half as big. We can literally throw that half of the problem away. Now we're left not with 1,000 pages, but say 500. So now what do? Well, a typical human will go roughly in the middle again, and I find myself at the R section, so not quite there. So again, I can tear this problem in half. Thank you. So now I only have some 250 pages, and I can do this again and again and again and go from 125 down to roughly 60 to 30 to 15 and so forth. And finally, I'll get whittled down to one of the S pages on which, if he's in the phone book, Mike Smith should be. Now, that's obviously a fairly reasonable algorithm, and it's a one-time use algorithm in this case, but what can we sort of take away from that? Well, the first approach, correct, if naive though it was, can be described by this straight line. So if on the x-axis here we say this is the size of the problem, so as the x-axis goes to the
All right, so let's take a look at this so you can see an example. You do not need to understand the code. In fact, I'm not even really going to go through what's going on in the code. I'm just going to explain what is happening. You just need to understand why this is more efficient in certain circumstances, especially when you have an array that has a plethora of information stored inside of it. So we have a list of numbers. Now, this is not a long list. A linear search would be perfectly fine on this list, but I'm not going to sit there and put together a list of 2 million things. Not going to do it. So it's going to kind of show you how this works. Pretty simple. So if you remember, the very, very, very first thing that you have to do in order to use binary search is you have to sort. Okay, and this would also be the case if it was strings as well. They need to be in alphabetical order. So in this case, we're going to be putting them in numerical order. Okay, that's what this function does right here. So this is going to sort it and put it into numerical order. So we're going to be looking at this down here. Okay, so this is our sorted list with compare numbers, that little function. You can see that it is in order. All right, then we have this function right here, binary search, is the little algorithm that is going to perform the search. Okay, and in a nutshell, essentially what is going on is it's looking at midpoints within the array and then eliminating giant chunks of the list if that target number or value that you're looking for is not in that section. So that's what's going on in the algorithm. Okay, so how does this work? So I'm calling the function right here, and I'm looking for, okay, if you look at my parameter up here, I'm looking for the target. Okay, so my target is 56. I want to find where the number 56 happens to be. So I gotta look at how many elements are there in this list. So I would run a length. Okay, so I want to know how many. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 16. I'm going to take the midpoint of that. So half of Half of 16 is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm looking at the number 34. My target number is 56. So I'm going to say, is 34 greater than or less than 56? Well, I know that 34 is less than 56, and this is a numerical value. So if it's in or numerical order. So if this list is in numerical order, everything to the left of 34, it can't be 56. So I can automatically then eliminate this whole chunk. So now I'm left with half the list. See how quick that was? Same thing. So now we're down to 8 elements. And so then I want to look at the middle element, which is 4. So 1, 2, 3, 4. So that's 66. So 66. Is 66 greater than or less than 56? So I know 66 is greater than 56. So because of that, and the fact that this list is now in order numerically, I know that 56 cannot be anything above 66. So then I can eliminate all of that. So now I'm left with these 3 values. The middle is 41. Well, is 41 less than or equal to, or sorry, less than or greater than 56? So it's less than. So because it's less than, it can't be anything that way. So then I can eliminate all of that. And boom, there's 56. That's how a binary search works. And like I said, on really long lists, it's super efficient. So you don't have to learn, do not have to know how to code this. You just have to understand why a binary search is more efficient than a linear search when it comes to large arrays of data. So here's what the AP people want you to know, the lovely College Board. This is what they want you to know about algorithms and searching and sorting and whatever. So I would look through this and see what you need to know specifically. Again, we're looking at algorithms efficiency, and you should look at like when choosing what algorithm you use, be it like a linear search or a binary search, that you use reasoning and thinking about it. So think about mathematically about the algorithm, which one is faster, which one is slower, which one's more efficient, which is less efficient, and so on. Okay, and then I know somewhere it actually says linear. Here's again a lot of stuff on efficiency. More efficient, sometimes more efficient algorithms are more complex. And I mean, definitely the binary search algorithm is more complex, but it is more efficient. You don't need to know about big O if you are familiar with that. Here it is right here. So this one in particular. So you need to know linear search can be used when searching for an item in any list. Binary search can be used only when the list is sorted, okay, either alphabetically or numerically. And then for this over here, for what we're doing here, this one is the relevant one. So the difference between linear and binary search in terms of process and efficiency. So with lesson 15, you guys get to code this again, but it'll be way easier. You're going to be creating, I think, a really cool generic function that you can find the minimum value on not just what you're going to be doing here, but on any list. So that's kind of neat. So then that brings us to what you're doing. So I need you guys to complete lesson 15, the entire thing. So 1 through 15. I didn't think this one was overly complex, but if you have any problems, you don't understand something, please let me know. So use Remind to ask me any questions. I'm pretty good about getting back pretty quickly. If I'm busy, I will let you know and I will get back to you. Okay, I don't think I've ever let anyone down if they had a question using Remind. So that really is it. I would like you guys to have this one done by Friday. Remember, guys, that the College Board hasn't changed anything yet. Their next update's supposed to be on the 20th, which is Friday. So if I have any new information to pass on, I will. And I hope you guys are awesome and that you are relaxing, but also, pushing forward and do a random act of kindness for somebody. Okay? Put a smile on face. All right, we'll see you guys, and I'm gonna leave it. You can watch it or not, but this is a kind of a bizarre video that I have on binary search where you have some dancers doing flamenco dancing and illustrating a binary search. So you can choose to watch it or not. Hope you guys are fantastic. And I shall see you sometime, hopefully soon. Take it easy. Easy. Bye.